everybody. In the last lecture, we discussed about covariance and correlation coefficient. Over here, we are going to discuss. We are going to continue the discussion. First of all, we are going to put a few results related to covariance, correlation coefficient, and standard deviation. What we are going to do is that at first we are going to calculate the variance of this quantity x plus minus y. What we have, we already know that expectation of x plus minus y is equal to mx plus minus my. Mx is the mean of x and my is the mean of y. So what we can say from this result, you see, if we consider that z is equal to x plus minus y, in that case we can say that the mean of this z, this m of z, can be written as the mean of x mx plus minus mean of y my. Therefore, we can say that z minus mz, this z minus mz is equal to x minus mx plus minus y minus my. Therefore, what we can now say that variance of x plus minus y, that would be is equal to the variance of z, and its formula is expectation of z minus m of z whole square. Now, in place of z minus m of z, we just put this expression x minus mx plus minus y minus my. Therefore, we have this type of expression x minus mx plus minus y minus my, its whole square. We are considering the expectation of this total quantity, and that can be expanded in this fashion, that expectation of x minus mx whole square plus expectation of y minus my whole square plus 2 plus minus 2 into expectation of x minus mx into y minus my. Now you can observe that this first term x minus mx whole square, its expectation is equal to the variance of x. This second term, that is expectation of y minus my whole square, that is equal to variance of y, plus minus this expectation of x minus mx into y minus my. This expectation is equal to covariance of x comma y. Therefore, we can write that variance of x plus minus y, that is equal to variance of x plus variance of y plus minus 2 into covariance of x comma y. Or in other words, we can say that sigma of x plus y square whole square, that is equal to sigma x square plus sigma y square plus minus 2 into, what is this? This rho into sigma x sigma y is nothing but is equal to this covariance of x comma y. Alright. Therefore, we can write this type of result, that this last term is equal to twice rho into sigma x sigma y. And this result can be extended further for in number of random variables. We generalize this result, and if we consider the linear combination of in number of random variables, say a1 x1 plus a2 x2 and so on, ultimately up to an x2 xn. If we call this the total summation is equal to Sn, then we can prove that the mean of this random variable Sn, the mean of this random variable Sn would be is equal to Mn, and that is equal to expectation of Sn, and that expectation would be is equal to actually expectation of all the summation of all this type of quantity, so that we can now write expectation of this total quantity, expectation of this a1, expectation of this a1 x1 plus a2 x2 and so on, and this can be further written as equal to the summation where I is equal to 1 to n ai into expectation of xi. All right, and this term can be further written as equal to this kind of summation, and in place of in place of this expectation of xi, we can write mi would represent this expectation of xi, or the mean of this of the random variable xi. And if we now write this kind of expression, sigma n square, it represents the variance of this variable in this random variable Sn. Then one can extend this previous result, and we can further prove that this variance is equal to summation I is equal to 1 to n ai square sigma I square plus 2 into this kind of summation, where this summation is actually extended over all possible values of I and j, over all possible values of I and j. And over here, just one restriction is that I should be less than j. So I and j are both varying from 1 to n, with the restriction that I less than n. Over this type of quantities ai aj sigma j multiplied by rho, that means the correlation coefficient in between xi and xj. Okay, so we can extend these results over here. And this is the first result that we wanted to discuss. And the second result that we wanted to discuss over here is that the correlation coefficient is independent of origin and scale. What is this? Actually, we already have proved this result in the previous class, that if u, this random variable u, is equal to, say, a1x plus b1, and v is equal to a2x plus b2. In that case, we proved this result, that the correlation coefficient in between u and v, this correlation coefficient is equal to a1 a2 divided by modulus of a1 and modulus of a2, multiplied by modulus of a2, and this is multiplied by correlation coefficient in between x and y. I'm sorry, I made one mistake over here. You see, this x, in place of this x, we should actually write y. So let me make this correction, that this should be is equal to y. So v is equal to a2y plus b2. All right, but now over here, you see what this type of transformation mean. U is equal to a1x plus b1. This transformation, this result can also be written in this way. You see, a1x, that is equal to u minus b1. Okay, and if we consider this one as equal to, say, suppose the third random variable, suppose z, in that case what we have, we actually have that z is equal to a1x. So this is actually multiplication by a scalar. And further, if we suppose that if this a1 is a positive quantity, then this would represent the change of scale of the random variable. Suppose, what does it mean? It means, suppose if x is represented in terms of centimeter, and z is represented in terms of meter, in that case, 1 unit of z would be related with 1 unit of x by what relationship? By the relationship that 1 meter, that means z, should be obtained by is equal to 100 times x, Or you can say that if the length of one rod is equal to suppose 50 centimeter, 50 centimeter. In that case, it is represented in terms of centimeters. So in terms of this x scale, and this 50 centimeter can be written as equal to 50 divided by 100 meter. Therefore, you see, division by 100 or multiplication by 100 would actually change the scale of the measurement. Therefore, over here we can say that this A1 multiplication by a non-negative scalar would actually represent the change in scale. Now over here you see u1 minus u minus b1 is equal to z. It actually means that u is equal to z plus b1. So if we add some constant or subtract some constant, what does it mean? It means that we are changing the origin. So altogether, this transformation u is equal to a1 x plus b1 would actually have both the effect, the change of origin and change of scale, provided that a1 is greater than 0. Okay, therefore if a1 is greater than 0, and similarly if a2 is greater than 0, if a1 is greater than 0 and a2 is greater than 0, in that case you see this relation, from this relation we can say that this relation would be is equal to a1 a2 divided by simply a1 a2 multiplied by rho in between x and y. Okay, in between x and y, and that is nothing but is equal to rho in between x and y. So what we observe is that the correlation coefficient in between x and y and the correlation coefficient in between the transform variable u and v. Transform variable refer to change of scale as well as change of origin in x and y. That's why we say that the correlation coefficient in between u and v is same as the correlation coefficient in between x and y. That means the correlation coefficient is actually independent of origin and scale of measurement. Okay, correlation coefficient is independent of the origin and scale of measurement. This is the second result that I wanted to discuss. Next, the third result that we shall discuss over here is this relation. That means the the covariance in between x and y, or this mu11. This expression is equal to alpha 11 minus mx into my. What is alpha 11? Alpha 11 is actually the raw moment. Alpha 11 is equal to this expectation in between x and y, and we know what is mx. Mx is equal to the mean of x, that is equal to expectation of x. Similarly, my, that is actually the mean of y, that is equal to expectation of y. So we shall again you see what is mu11. Mu11 is equal to actually the covariance in between x and y, and what is this? This is equal to expectation or in between expectation of this type of expression, x minus mx into y minus my. Okay, so it's my. All right, so if we expand this one, you see this expansion, this will give us this type of expansion, that xy minus x into my minus y into mx plus mx my. All right, expectation of this total quantity, and that would be equal to expectation of x y minus my. This is actually constant, so we can take it outside this expectation symbol. So that would be expectation of x minus mx into expectation of y plus expectation of mx and my. All right, and we know that expectation of mx and my is nothing but is equal to that constant mx into my. So we can write this term as equal to expectation of xy minus this my into this mx is this expectation of x is equal to mx minus this mx into this my plus this expression mx my. So we can cancel this term with this term. All right. So after cancellation, what we got, we get this result that could be is equal to expectation of xy minus mx my. mx my. Okay, so we get this result that expectation of xy that is equal to this quantity alpha 1 1 minus mx into my. Okay, so we prove this result that mu 1 1 is equal to alpha 1 1 minus mx into my. So this is the third result that I wanted to discuss over here. Now, a theorem that we are going to prove in this lecture is that suppose we have a transformation which is actually the combination, which is actually the rotation in two-dimensional plane. So if x and y, if we have a joint random variable x and y, and we are transforming it to another pair of random variables u comma b by this type of transformation formula. U is equal to x cos x plus y x cos alpha plus y sin alpha, and v is equal to minus x sin alpha plus y cos alpha. So this actually refers to the rotation of the coordinate axis by an angle alpha in the anti-clockwise direction. And this result says that if u and v are uncorrelated means that they are linearly uncorrelated. That means there is no relation in between. There is no linear relation in between u and v, so that the covariance in between u and v is covariance u and v. The covariance in between u and v would become is equal to 0. So from this result, we shall have to show that tan of twice alpha is equal to twice rho into sigma x sigma y divided by sigma x square minus sigma y square. So we shall have to show this result from the fact that covariance of u comma v is equal to 0. So let us prove this result. So over here we suppose that these are the given relations u is equal to x cos alpha plus y sin alpha, and v is equal to minus x sin alpha plus y cos alpha. Then what we are given, that we are given that u and v are uncorrelated. Now u and v are uncorrelated, we shall have to show this result. And what is rho? Rho actually refers to the correlation coefficient in between x and y. All right. Now what we have, we actually have this type of relation: u is equal to x cos alpha plus y sin alpha. So if we take the expectation on both sides, in that case we shall have expectation of u that is equal to m of u plus expectation of x that is m of x into cos alpha plus expectation of y that is equal to m of y into sin alpha. And similarly, from this second relation, we shall have this relation m of v is equal to minus mx sin alpha plus my cos of alpha. So we have this type of relation. Therefore, you see, so if we subtract this m of u from this expression of u, then we can take this cos of alpha common, and after taking this expression cos of alpha common, we shall have within bracket x minus m of x. Similarly, from this second terms, we can take sine of alpha common, so that we shall have y minus my into sine of alpha. Similarly, we can have this relation b minus mv is equal to minus of x minus mx sine alpha plus y minus my into cos of alpha. Therefore, now if we multiply these two expressions, this right hand side expressions over here, in that case, what we have, we have this type of relation that u minus mu multiplied by v minus mv. This expression is equal to x with this negative sign, x minus mx whole square with this negative sign, x minus mx whole square into cos alpha sin alpha. Again, this term can be multiplied by this term, then we shall again have a cos alpha and sin alpha term. So, and its coefficient will be y minus my whole square. And the remaining terms will together construct this term, that x minus mx into y minus my into cos of twice alpha. Actually, we shall have cos square alpha minus sin square alpha. That can be combined, that can be written as cos of twice alpha. Okay. Now, if we take the expectation on both sides, then what we have, and before taking the expectation, we can again convert this cos alpha sin alpha, this type of expression, into half of sin twice alpha, so that within bracket we can write this kind of expression, x minus mx, this y minus my whole square minus of x minus mx whole square. Okay. So we actually have this type of term, and this remaining term in this third term will remain unchanged. Okay, x minus mx into y minus my into cos of twice over here. This is cos of twice. Now, if we take the expectation on both sides, on the left side we shall have the covariance of u comma v, and on the right side we shall have the expectation of this first term, expectation of this type of term, y minus my whole square. So this y minus my whole square, its expectation will give us sigma y square, and this x minus mx whole square, its expectation will give us this sigma x square, and expectation of this type of quantity, expectation of x minus mx into y minus my, it will give us the covariance of x comma y. Okay. So if further but by question, if it is given that this covariance becomes equal to 0, then we can say that this right hand side expression would be equal to 0. And from this result, you see covariance of x comma y, that can be written as rho into sigma x into sigma y. And therefore, from this result, we can easily compute the expression of tan alpha. So we can compute, or we can make cross multiplication, then sin alpha divided by cos alpha will give rise to this expression of tan twice alpha. Sin twice alpha divided by cos twice alpha will give rise to this expression of tan twice alpha. So tan twice alpha is equal to, this is a straightforward computation, that would be is equal to twice rho into sigma x sigma y divided by sigma x square minus sigma y square. So we have this relation over here. And now let us consider some cases when capital X and capital Y are independent random variables, and we are going to study the effect of independent random variables, the effect of independent random variables over the expressions of different kind of mean value or different kind of expectations. Alright, so first result that we are going to study over here is that if x and y are independent random variables, then expectation of g1x multiplied by g2y, this expectation can be written as expectation of g1x multiplied by expectation of g2y, provided of course these two expectations exist. Okay, and this rule is actually sometimes referred to the multiplication rule of expectation. So multiplication rule would be valid only when we have independent random variables. So we start this result with considering the continuous random variables, and in case of continuous random variables, the expectations of this expectation of g1x will be equal to this type of integral from minus infinity to infinity, g1 of small x multiplied by the corresponding marginal density function of x, that is actually fxx into dx, and this expectation of g2y, that would be equal to this type of infinite integral minus infinity g2y multiplied by the corresponding marginal density function fyy, okay, dx. So you see, in this as per the definition of these two expectations, these two infinite integrals, these two infinite integrals must be absolutely convergent. Okay, these two infinite integrals must be absolutely convergent, and if they are absolutely convergent, then the existence of these two integral will together imply the absolute convergence of their product of their product, and that product can be written as equal to double integral from minus infinity to infinity, from minus infinity to infinity, g1x multiplied by g2y, then multiplied by corresponding probability marginal density functions, fxx into fyy dx dy. That's why we start with this right hand side. We start this proof from this right hand side, because existence of these two quantities will imply the existence of this product, the multiple integral, and that product would be is equal to this type of product. And as because capital X and capital Y are independent random variables, therefore this product of these two marginal density functions would be is equal to the joint density function of x comma y, and in that case this multiple integral would be is equal to expectation of g1x multiplied by expectation of d2y. So this is the proof of this result when capital X and capital Y follow the continuous distributions. Now, even if these two are not continuous, in that case also we can prove this result by a similar fashion. Over here, you see we are discussing the proof when these two random variables are discrete random variables. So over here you see expectation of g1x. Expectation of g1x would be is equal to the infinite summation. Over here I should vary from minus infinity to infinity. So expectation I is equal to minus infinity to infinity g1 of xi multiplied by f xi. Okay, this is the marginal mass function of x. Similarly, expectation of g2y, that would be is equal to the summation over j should vary from minus infinity to infinity. G2 of yj, f of yj, f yj refers to the marginal mass function of y. Okay, again you can say that as per the definition of these expectations, these two infinite series must be absolutely convergent, and absolutely convergence means their product would also be absolutely convergent, and then this product can be written by this type of double summation. Over here you see capital X and capital Y are independent, therefore this expression, this fxi fyj, this expression would be is equal to this. This is the mass function of the marginal density, marginal distribution of x, and this is the mass function of the marginal distribution of y. And if x and y are independent, in that case this product would be is equal to the probability mass function of the joint distribution of x and y, that is actually fej. Therefore, in place of this term fxi into y fyj, we can write this expression fij, and in that case this expression would be ultimately is equal to the expectation of this g1x and g2y obtained from the joint probability distribution. So we actually have this type of result, expectation of g1x multiplied by expectation of g2x, that is equal to the double summation of double summation of g1xi multiplied by g2yj multiplied by this fij, and that is equal to the expectation of g1x into g2y. So this is known as the multiplication formula of expectation, and this is true only when x and y are independent random variables. As a special case of this result, we can prove this result that if capital X and Y are independent, in that case expectation of x, y can be written as expectation of x multiplied by expectation of y. So these are all multiplication rules, and you can extend this result. You see over here, we can prove this similar result, that if capital X and capital Y are independent, capital X and capital Y are independent, in that case we can write this type of quantity mu ij, hmm, mu ij, that would be is equal to expectation of this type of term x minus mx to the power of I into y minus my to the power of j, and that would be can be written as by this multiplication rule. This can be written as expectation of x minus mx to the power of I multiplied by expectation of y minus my to the power of j. So this would be is equal to this first factor. This first factor would be equal to the ith central moment. Therefore, we can write ith central moment for x. Therefore, we can write mu xi, and that the second factor, this second factor, will be is equal to the jth central moment obtained from the distribution of y. Therefore, we can write mu yj. So this is the consequence of the multiplication rule when capital X and Y are of course independent random variables. Okay, so, and similar result holds if we consider the raw moments. Therefore, we can write alpha ij, that is equal to this expectation of x to the power of I y to the power of j, and by multiplication rule we can write this one as simply expectation of x to the power of I into expectation of y to the power of j, and this first factor would be is equal to alpha xi, the ith raw moment obtained from the distribution of x, and the second factor would be is equal to alpha yj, that is actually the jth raw moment obtained from the distribution of y. Okay, so in this way we can obtain the different relationship involving this kind of central and raw moments. All right. Now we are going to discuss. We are going to continue this discussion by defining what is called the characteristic function. What is this characteristic function? The characteristic function in the joint distribution of x comma y is actually a function of two real variables t and u. Okay, the characteristic function is actually a function of two random variables t and u, and which is defined in this way that chi of t comma u is equal to expectation of e to the power of I multiplied by tx into ty. So this is actually the definition of characteristic function in the joint distribution of x comma y. All right, and in this from this result we can now deduce a result that is called the reproductive property of the characteristic function. In order to show the reproductive property of this of the random variables, we can first consider the statement of this proof. Only the statement, we don't need the proof of this theorem. It says that necessary and sufficient condition for the random variables x1, x2, xn. All right, we have n number of random variables to be mutually independent is that their joint characteristic function. Over here, you see, we are considering the joint characteristic function. We already defined the characteristic function for two random variables, x and y. And there we had two real variables, t and u. Alright, but over here we have n number of random variables, x1, x2, xn. That's why we have n number of real values, real variables t1, t2, tn in place of t and u. Initially, in the definition of characteristic function, we had only two random variables, and that's why we had only two real variables t and u. But over here, we have n number of random variables. That's why we have n number of real variables t1, t2, tn. Okay. So this characteristic function of x1, x2, this x1, x2, xn, that would be is equal to the product of their individual characteristic functions. That means the characteristic function of x1 multiplied by characteristic function of x2 multiplied by characteristic function of xn. Okay, so this is the first result. We don't need the proof of this result. The proof is straightforward. And from this result, we can now prove the second result, that is actually known as the reproductive property of the characteristic function. What does it say? What does it say? It says that if we have this summation Sn is equal to summation of all these random variables, all these mutually independent random variables. Mind it, these random variables should be mutually independent. So Sn is equal to x1 plus x2 plus dot plus xn. Okay, plus xn. So this is the summation of all these random variables. If Sn is defined in this way, then we can prove that characteristic function of this single random variable. All right, as because there is a single random variable, therefore the characteristic function will have only a single real variable t. So this characteristic function a of t of this summation Sn, by definition, this characteristic function would be is equal to expectation of e to the power of it into Sn. You can recall the definition of characteristic function for a single random variable. So this is the definition of characteristic function for a single random variable. So by this definition, if we put Sn is equal to this type of expression, x1 plus x2 plus xn. Okay, so we are putting x1 plus x2 plus xn, and then we can write this type of expression as equal to e to the power of it into x1 multiplied by e to the power of it into x2 multiplied by e to the power of it into xn. And as because x1, x2, xn are mutually independent, therefore by multiplication rule of expectation, we can expand this, and we can write this as equal to the product of individual expectations. So like expectation of e to the power of it x1 multiplied by expectation of e to the power of it x2 multiplied by expectation of e to the power of it xn, and so on. So what is this? This first factor. This first factor is actually the characteristic function of the first variable x1. This second factor is the characteristic function of this second variable x2. This last factor is actually the characteristic function of this last random variable xn. Okay, so in this fashion, we can prove that the characteristic function of this summation Sn. All right, the characteristic function of this summation Sn can be is equal to the product of individual characteristic functions, provided, of course, this x1, x2, xn are mutually independent. We need to keep in mind that over here, this x1, x2, xn has to have to be mutually independent random variables. So this is the reproductive property of the characteristic functions. And in this reproductive property, using this reproductive property, we can apply this reproductive property of the characteristic functions in case of binomial distribution, Poisson distribution, and any other kind of distributions. Over here, we are going to discuss the reproductive property, and we are going to apply this reproductive property to binomial distribution, Poisson distribution, and normal distributions. We are going to show this result in case of binomial, Poisson, and normal distributions over here. So you see over here what we can prove. You see, you can consider this binomial distribution. We know that the characteristic function of a binomial in p distribution. Over here in place of n, we are considering n this parameter nk. All right, because we shall have to deal with n number of binomial variates. So over here we are considering this kind of n number of binomial variates. Like you can say that this if x is a binomial np-variate, n comma p-variate, but in place of x we are actually having n number of random variables like x1, x2, etc. dot 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 up to xn. So what we had in the previous chapters, we already put this result that that this kind of binomial that this is actually the characteristic function. So over here the characteristic function of this random variable x, the characteristic function of this random variable x would be is equal to I of t, that is equal to p into e to the power of I t plus q whole to the power of n, where q is equal to 1 minus p. So this was the characteristic function for a binomial np variate. Now in place of this n, you see if x1 is a binomial variate, then its parameter would be is equal to n1 comma p. Okay, we are just changing this number n, we are not changing this probability of success p. The parameters of x2, we consider the parameters of x2 is equal to n2 comma p. Similarly, we consider the parameter of this xn to be is equal to not xn, rather we consider x capital N, x capital N. All right. So its parameter would be n capital N comma small n suffix capital N comma p. And in that case, what would be the characteristic function of x1 or x2 or x3? In general, the characteristic function of xk. So if we have xk, then its parameters are nk comma p for k is equal to 1, 2, dot 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 up to suppose capital N. And in that case, its corresponding characteristic function should be is equal to chi kt, that is equal to p into e to the power of it plus q whole to the power of nk for k is equal to this type of expression. So if we have Sn, alright, Sn is equal to the summation of all this type of random variables x1 plus x2 plus dot 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 plus x capital N. In that case, what will be the characteristic function? By the reproductive property, the characteristic function of this Sn, let us simply denote it by chi of t, that would be is equal to the product of all this type of characteristic functions. So we should write product symbol, product, k is equal to 1 to capital N of this type of I k t. So over here, if we just put their expressions, that over here we shall have product symbol k is equal to 1 to capital N, and then we can write p into e to the power of I t plus q to the power of this nk. All right, and so as because we have the product, therefore this expression can be written as p plus p into e to the power of I t plus q whole to the power of, over here we shall have summation of nk, and this summation of nk, you see this summation of nk can now be written in this way: e to the power of summation over k is equal to 1 to capital N multiplied by n k. So this would be the characteristic function of this type of summation x1 x2 xn. So in this way, we can compute the characteristic function of the summation of n number of binomial random variables. So this similar result holds if we consider the Poisson variate. You see, we already know that in case of Poisson distribution, say if suppose capital X is a Poisson variate with parameter mu, in that case we can prove that the characteristic function is equal to phi t, that is equal to e to the power of mu, and in this exponent let me write it in this fashion, e to the power of mu, and in this exponent we shall have e to the power of it minus 1. This is the characteristic function of a Poisson mu variate. So now over here, suppose we have n number of mutually independent Poisson variates x1, x2, dot 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 xn, and the parameter of x1 is equal to suppose mu1, the parameter of x2 is equal to suppose mu2, the parameter of xn rather is equal to, we consider mun. All right. So what would be the parameter of this kth random variable? That would be is equal to mu k. Therefore, its parameter can be written as, this characteristic function can be written as phi kt is equal to e to the power of mu k into e to the power of it minus 1. So now if we suppose Sn is equal to the summation of this x1, x2, xn, plus dot dot dot, say this xn, in that case by reproductive property, what we can say, the characteristic function of this random variable Sn. So let us denote it by characteristic function chi of t, that is equal to the product of the characteristic function of all these individual random variables x1, x2, xn. So we can say that would be is equal to product of chi k t, and there we shall have k is equal to 1 to n, and therefore this can be written as product of e to the power of mu k into, within this exponent we shall have e to the power of it minus 1. Okay, this type of expression, and that would be is equal, over here k should vary from 1 to n, and after multiplication this expression would be is equal to e to the power of, what we shall have, you see, e to the power of it minus 1 multiplied by this summation mu k, k is equal to 1 to n. So in this way we can find the reproductive property of Poisson distribution. All right. So now you see, if we have, we can consider the same type of proof for normal distributions, but over here we are rather considering a more general expression. Say we are considering this type of linear combination in case of normal distributions. So we consider a sequence of normal distributions, a finite sequence, or you can say we consider a finite number of mutually independent normal variates x1, x2, xn, and their parameters or the mean values are m1 into mn, and their standard deviations are sigma 1, sigma 2, dot dot dot, sigma n. These are the parameters of the normal variates, and we consider a variate, this type of variate with a1 x1 plus a2 x2 plus an xn. So over here, what we find is that mx would be is equal to their linear combination a1 into m1 plus a2 into m2 dot 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 plus a into amn, and as because x1, x2, xn are mutually independent, we shall prove. We can prove that the variance of this random variable x, variance of this random variable x would be equal to a1 square sigma 1 square plus a2 square sigma 2 square dot 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 plus an square sigma n square. We would not have any type of this type of term, rho twice rho into sigma x or sigma x1 or sigma x2 etc. This type of term would not appear because of the fact that all these x1 x2 xn are mutually independent. So this type of terms would actually vanish. All these terms would be is equal to 0. So we shall have this type of result. Got it? And from this relation we can prove that characteristic function. We know that characteristic function of this type of random variable, this type of variable having following the normal distribution. The characteristic function can be written in this way: it is equal to e to the power of I m t minus half sigma square t square. So over here we are actually dealing with this type of random variables x1, x2, xn. So if we consider a representative random variable xk, okay, and suppose in that case its corresponding characteristic function would be equal to chi k, and the parameters are mk and sigma k. So in this way we can have the expression of this chi t, and from this expression you can easily compute the characteristic function of this a1 x1. Okay, firstly we can easily compute the characteristic function of this a1 x1, then a2 x2, and then an xn. How can we compute this result? We can say that the corresponding characteristic function would be is equal to chi k of a1t, and that would be is equal to e to the power of I a1 ak into nk t. Just in place of t we are putting ak into t. So we have the similar type of relationship, and from the reproductive property we can easily prove that this chi k, that the characteristic function of this random variable x is equal to this chi xt is equal to e to the power of I mxt minus half sigma x squared t, where this mx has this type of relation and sigma x has this type of relation. We are leaving the entire detailed computation as a homework to you. Okay, and what is the final gist of this total discussion? The final gist what we have, let me just summarize the result over here. What we got is that in case of binomial distribution, in case of binomial NP distribution, what we observe is that if x is a xk, or particularly speaking, if xk is a binomial variate with parameters nk comma pk, then the characteristic function of this Sn, what was Sn? Sn was equal to x1 plus x2 plus dot 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 plus xn. This characteristic function of was given in this fashion: chi t, that is equal to e into e to the power of I t plus q whole to the power summation in k. Okay, now if we suppose that this summation nk, if we designate this summation of nk by mu, suppose mu is equal to this kind of summation nk. The summation is taken over all possible values of k. Summation is taken over all possible values of k. In that case we can write as this is this kind of mu, so that we can now conclude from this expression of this characteristic function, we can conclude that Sn is a binomial variate with parameter nu, comma p. Okay, with parameter nu, comma p. So this is one result. In the second result, in case of Poisson distribution, if xk is a Poisson variate with parameter mu k, in that case this characteristic function of this kind of random variable Sn, in that case the characteristic function of this type of random variable Sn would be is equal to chi t, and that chi t is eventually proved to be is equal to x e to the power of it minus 1 into this type of summation of mu k. And further, if we simply represent this summation of mu k by is equal to the notation mu. So if we suppose that mu is equal to summation of this type of expression mu k, where summation is taken over mu, in that case we observe that this would be the characteristic function of this type of summation Sn. So what we observe that in this case also we can conclude that Sn is Poisson mu variate. So what we observe, similar result can be deduced for other random variables as well. So what is observed that as an application of the reproductive property of the random variable, we can say that if these variables follow a distribution, in that case the corresponding summation, this type of summation would also follow similar distribution, and the parameters of that distribution will be actually obtained by this type of summation formula. So this is actually a binomial NP variate, where binomial nu comma p variate, where this nu is obtained by the summation of this nk. Similarly, in this case, this Sn is actually a Poisson mu variable, where mu is actually the summation of this type of mu k. So similar result holds in case of Poisson distribution, in case of similar other distributions. So as a homework, we are leaving one such result to prove the characteristic property, or to apply the reproductive property of characteristic function. To apply, I am leaving this one as a homework. Okay, to apply the reproductive property of the characteristic function on chi-square distribution. We already discussed chi-square distribution in the previous chapter, so I am not showing the detail. So this is the homework for the students. So that's all for this lecture. Thank you for being with us.